in which an acid forms H plus in solution and a base forms OH minus, right? And then the Bronsted-Lowry definition, in which an acid is a proton donor and a base is a proton acceptor, right? And then we started learning about strong and weak acids, right? And we learned about Ka, the acid ionization constant, right? The acid ionization constant is just the equilibrium constant, right, for the ionization of an acid, all right? And we saw a table with a lot of Kas for different acids. That table is in your book. You may need to use that table as you work through problems on the problem set. Okay, you might have to look up those Kas. We talked about the auto-ionization of water and how water acts as an acid and base with itself, right? And we saw how that determines pH, and we saw the definition of pH, right? And I think we ended it last time with the idea that there was 4 quantities that if you know one, you know them all, right? pH, pOH, H3O plus concentration, which by the way is the same thing as H plus, right? Those are completely interchangeable, and OH minus concentration, yeah? And the important relationships there are that H3O plus times OH minus, when you multiply those together, that equals 10 to the minus 14, right? So if you know one of those, you know the other. And then the definition of pH minus the log of the H3O plus concentration, right? And then the relationship that pH plus pOH is equal to 14, right? So these relationships allow you to quickly and easily interchange between these 4 quantities, okay? And we'll be using those 4 quantities quite a bit, so it'd be important for you to be able to go back and forth, okay? All right, so now what we want to do is we want to say, okay, now that we know these quantities, how do we determine them? How do we determine the pH of a strong acid and a weak acid? All right, so we're here finding H3O plus in acid solutions, all right? So it turns out a strong acid is fairly straightforward. In a strong acid, remember, like HCl, for example, right? When we write the equation, it goes all the way to the right, forms H3O plus Cl minus, okay? Remember, this is one of those equations that I gave you, right? I gave you 2 equations. I even included them in the email that said these equations you should just have on the back of your hand anytime, ready to go, right? But this goes all the way to the right. What does that mean? That means if I have a 1 molar solution of HCl, right? Or let's say a 0.1 molar solution of HCl. 0.1 molar solution of HCl means that I have 0.10 molar of H3O plus. So for a strong acid, the concentration of H3O plus is just equal to the concentration of the HCl. Now, that's true 99.9% of the time, and it'll be true 100% of the time in this class. But be warned that there is another contributor to H3O plus in water that we're not going to have to worry about, and that's water itself. So water itself, right, is in equilibrium with H3O plus OH minus, right? And so this reaction actually contributes a little bit of H3O plus, right? But remember, in a neutral solution, how much does it contribute? We know that amount. It's 1 times 10 to the minus 7 molar, right? We saw that last time, okay? That's because Kw is 10 to the minus 14. That's a very small number compared to the amount that's going to come, let's say, from a strong acid like HCl, okay? And not only that, but when HCl forms H3O plus, it's going to push this equilibrium to the left and make that contribution even less, right? So the bottom line is this. For a strong acid, if you want to know the concentration of H3O plus, all you got to do is look at the concentration of the acid, and they're identical, okay? Because it completely ionizes. You can completely ignore water. The only time you can't ignore water is for very, very dilute solutions, and we're not going to worry about those in this class, okay? If you take upper division chemistry classes later, you'll see that. And I don't want you to say, hey, Dr. Tro lied to me. No, I just oversimplified things a little bit, okay? So if I have a 0.1 molar HCl solution, right, then the pH of that solution is just minus the log of 0.1, right? And that's equal to 1, Okay, so that's super straightforward, right? Now, weak acids are a different story. And remember, I asked you to memorize 6 strong acids, right? HCl, HBr, HI, HClO4, HNO3, and H2SO4, right? So this idea applies to all of those. There are some cases in which it doesn't apply to H2SO4 because there's a 2 here, but we'll talk about that a little bit later, okay? All right, what about weak acids? Weak acids, if you have a 0.10 molar HC2H3O2 solution, the pH of that solution is 2.87. Okay, I'll give it to you here. So notice that the pH is quite a bit higher than the strong acid of the same concentration, right? Why is that? Well, it's because in the strong acid, this completely ionizes, right? In the weak acid, when we write out our equation, again, this is the equation that you have in your back pocket, right? H3O plus C2H3O2 minus, right? Notice the same equation, we're writing it over and over again. We're going to be using that equation quite a bit, right? But in this case, right, there's some of it ionizes, but a lot of it remains as HC2H3O2 minus, okay? So in order to find the concentration of H3O plus in a solution of a weak acid, guess what we have to do? Solve an equilibrium problem. Are you guys having some connection issues? Okay, my internet seems to be working okay. Seems to be working fine. So maybe it's
every now and then you kind of like cut off a little bit, but other than that, it's fine.
Okay. Okay, if it cuts off for a long time, just text me and I'll repeat things. Okay. So when you have a weak acid, you got to solve an equilibrium problem. So I'll just show you how to set up one for a generic weak acid, and then we'll do an example. Okay. Let's see what's next. Yeah. Okay. So if you have a generic weak acid, HA, right? Again, here's your generic equation, right? Again, this is the 3rd time I'm writing this equation so far in the first 5 minutes. That's how important it is. You're going to be using this equation over and over and over, right? You're going to, let's say you have 0.10 molar of this weak acid, okay? And you want to find the pH. Guess what? You got to solve an equilibrium problem, right? And that involves making an ice table, right? So this is 0.1, 0, 0. Now we know those aren't really exactly 0, but that's what we can ignore, right? In all problems that you'll do in this class, okay? And then this is going to be minus x, plus x, plus x, right? So this is going to be 0.10 minus x, x, right? The expression for Ka is equal to the concentration of H3O plus times the concentration of A minus all over the concentration of HA, right? So then you just plug these things in, right? This goes here, that goes there, that goes there, right? And you get, guess what, a quadratic equation. X 0.10 minus x is equal to x squared over 0.1 minus x, all right? Now, for many of these acids, since they're weak and since they have small equilibrium constants, for many of them, you will be able to make the x's small approximation, okay? So that'll be the case for many of them, but not all of them, okay? Not all of them. So let's look at a couple of examples. All right. So what's the pH of a 0.012 molar nicotinic acid? And by the way, you can write these formulas like this, right? Here's the weak acid, right? The basic formula is always going to be HA, right? So that A is that, okay? And then we have the initial concentration, right? So we got to write the equation HC6H4NO2 plus H2O in equilibrium with H3O plus C6H4NO2 minus, right? Again, that same equation again, okay? And then we set up our ice table, 0.012, 0, minus x, x, 0.012 minus x, and x. Right? So then you plug into the equilibrium expression, and let's see, Ka is given here. Ka is equal to 1.4 times 10 to the minus 5 is equal to the concentration of H3O plus times the concentration of C6H4NO2 minus divided by the concentration of HC6H4NO2, right? And then we plug that in there, and that in there, and we get x squared over 0.012 minus x is equal to Ka. All right, let's see. This is pretty small, so let's see if we can make the x a small approximation. We'll make that equal to 0, and then we'll get that x squared is equal to 0.012 times 1.4 times 10 to the minus 5. So x is equal to the square root of that product, and you get that x is equal to 4.1 times 10 to the minus 4, right? And then we should check to make sure that the x is small approximation is valid, right? So the way to check it, right, is say, okay, is x small compared to the number you subtracted it from, right? So I'm going to go 4.1 times 10 to the minus 4 divided by the number I subtracted it from is 0.012 times 100%, and I find that that's 3.4%. Right, and what I say, anything under 5% is good, so we're good to go on the x is small, right? So we can use this for x, and then we can get the concentration. So the concentration of H3O plus is just equal to, oh, my pen is running out. The concentration of H3O plus is just equal to x, so that's 4.1 times 10 to the minus 4, right? And then the pH is equal to minus the log of that. So that's equal to 3.39. Does that make sense? Let's see, I see a couple questions. No H2O. We don't include H2O. And I've been lazy here, right? It's a liquid, right? So this is aqueous. This is aqueous. This is a liquid. This is aqueous. This is aqueous, right? So liquids do not get included in the equilibrium expression. Okay. And what's the other question about it being minus 5? I'm not sure I understand the question about minus 5.
I think he's talking about the
exponent.
One more time.
The exponent, I think it's -5, not -4. Right.
Here?
Yeah. Right. If you the number from.
Oh, yes. Thank you very here. No. Here.
It's -4 when you multiply them.
Oh, to figure out the percent. And then it switches down over.
Once you multiply it by the 0.012, it'll turn to negative. The exponent will turn to -4.
Oh, okay, gotcha. Okay.
So I think it's correct, right?
Yeah.
Okay. Yeah, usually the equation will imply when it's a liquid, when it's a pure liquid, those aren't included, right? And so whenever you see water, that's always going to be a pure liquid. Okay. Okay, very good. Let's see, that's just the same thing I just worked out. Okay. Now let's try another one. In this case, we have another weak acid. Don't confuse this acid with HClO4, which is a strong acid. Okay. Was there a question, Taylor? Did you have a question?
Yeah, I was just for the KNAs, is there like a range of like where they sit? Like 10 times 10 to the negative
Yeah,
2.
it's like, yeah, 10 to the minus 2 all the way to 10 to the minus 12.
Okay.
Yeah.
Okay. It's just not the extremes. Or like
Right. Yeah. So that the really small ones, the smaller they are, the more likely you can make the extra-small approximation. I'm going to do one here where you can't make the extra-small approximation, as you'll see.
yeah, it's a much bigger number than the other two. Okay.
Yeah.
cool.
Yeah.
Okay.
Yeah. Okay. So in this case, we got HClO2. We're going to do the same exact equation, right? HClO2 plus H2O in equilibrium with H3O plus ClO2 minus, right? Again, you want to get to the point where you can write that equation out in your sleep for any acid, right? And we got 0.100 molar HClO2, right? And we're given Ka as being equal to 0.011, which is the same thing as 1.1 times 10 to the minus 2. Okay. So we set up our ice table. Again, this is going to start to look familiar, right? 0.10000 minus x. Again, the water is a pure liquid, so we ignore it. 0.100 minus x. So we have x squared over 0.100 minus x is equal to Ka, 0.011. So just for funsies, let's try making the extra-small approximation and see what happens. We get that x squared is equal to 0.100 times 0.011, right? And we get that x is equal to 0.033. So let's check to see if the extra-small approximation was valid. We take x and we subtract it from that number, right? So we got 0.033 divided by 0.100 times 100%, and we find that that's 33%. So therefore, the extra-small approximation is not valid. So in that case, we go back to our quadratic. X squared over 0.100 minus x is equal to 0.011. Okay. So if we multiply this out, we get something like x squared is equal to 0.011 times 0.100 minus x. And if we multiply that all out and get the quadratic form, we get x squared plus 0.011x minus 0.0011 is equal to 0, right? So there's my quadratic equation. And then I got to solve it using the quadratic formula, okay? I get two answers. I get x is equal to 0.028, or x is equal to negative 0.039. All right, we throw out the negative one, right? Because we know that concentrations can't be negative. So we know that x is equal to that. So the pH is equal to, H3O plus is equal to 0.028 molar, and pH is equal to minus the log of that, which is 1.55. Does that make sense?
I have a question.
Yeah.
When we're looking at the percentages, what does that tell us exactly?
So that tells us if this approximation is valid, the extra-small approximation. So the x,
Small percentage?
pardon me?
Does it have to be a small percentage for it to be valid?
Correct. It has to be under 5%.
Okay.
Has to be under 5% for it to be valid. So if it's over 5%, that means you got to work out the quadratic. If it's under 5%, then you don't have to. And,
Okay, thank you.
and remember, So I showed you guys how to do quadratics on Wolfram Alpha. Right, so you can go to Wolfram Alpha, you can do them that way, or if you have a calculator that solves them, you can do it that way, or if you want to just work it out every time, you can do it that way as well, okay? You'll have all those options, even on an exam. Correct, we're just solving equilibrium problems again, right? This is still, that's why I said we're going to be doing equilibria for a while, so we're going to kind of apply that concept to many different kinds of circumstances. Okay. All right. Very good. Very good. Very good. Very good. All right. You guys ready to try one? Sorry. I'd rather work these out. Okay. Here we go. Here's a question for you. Let me stop you for a minute. Let me give you a little bit of a clue on this one. Okay. So remember what we're doing. Let's go back to this. Can everybody see my screen here? Go back to this problem right here. Remember, the x is small approximation means you subtract x from this number. And what is this number? It's the initial concentration, right? So let's think about the x is small approximation for a minute. If I'm weighing myself and I weigh myself with and without a penny in my pocket, is the penny going to make a difference? No, right? It's not. Why? Because I weigh a lot more than the penny. Okay, so the penny doesn't matter. So what makes the penny small is the value of k, right? The smaller the k, the more likely it is that the x is small approximation is going to work. But there's something else we have to consider too. We have to consider the weight of me, right? What if I only weighed half a pound? What if I was a miniature Professor Tro and I only weighed half a pound? And then you weighed me with and without a penny, right? Then the penny would make a big difference, right? So the other thing you got to compare is this initial concentration. And in order for the x is small approximation to be large, right? You want a big initial concentration, right? So you got to look at both of the things. You got to both look at the weight of the penny, which is determined by k, and the weight of the thing you're subtracting it from, which is determined by that initial concentration. Okay? So given that, which one of these do you think the x is small approximation is least likely to work for? So right away, I see that most of you eliminated B and D. That's good because those have small k's, right? Small k's, typically x is small works. These have a little bit bigger. So between these two, which one is it less likely to work for, A or C? For the size of the penny is the same because the k's are the same for both of them. But look at the weight of the thing you're subtracting it from. Right? This is like a normal size Professor Tro. This is like a mini one, right? So, and I see you guys kind of split on those two, but that's the idea, okay? I'm going to end this here. Most of you answered and you split between those two. But the right answer is A, right? that small initial concentration is a warning sign that the X is small, it may not work. Okay, but again, you could always just try it and then compare and see what you get, right? And if you get less than 5%, you're done. If you get more than 5%, then you have to work the quadratic. Okay, here is a question for you to work out in detail now. So why don't you try this one? This one is one where you gotta find the pH. Oh shoot, sorry, hold on. Okay, there you go. And by the way, since you don't have the total formula of this one, just call it HA, right? Just call it HA. And to set up the ice table, what equation you're going to write? The same one we've been writing over and over and over, right? The same one that I emailed you in this week's list. That equation is your best friend. One of your best friends. Okay, try to finish up the next 15 seconds or so. All right, very good. I'm going to stop it right there. And most of you got the right answer, which was D. Nice work. Really briefly here, you write the equation for the ionization. In this case, I'm just going to use A because I don't know the formula. But you can just always write it this way if you wanted to. Plus A minus, right? And then you have your ice table. Put your initial concentration here, right? 0, 0, minus X, plus X, plus X, 0.25 minus X, X, and X. So you get X squared over 2.25 minus X is equal to Ka, 3.16 times 10 to the minus 4. I see that Ka is pretty small, and my initial concentration is not too small. So I'm going to try the X is small approximation. And I get that X squared is equal to 0.25 times 3.16 times 10 to the minus 4, right? So X comes out to be equal to 8.89 times 10 to the minus 3. I could check my approximation. How do I check it? I divide this number by the number I subtracted X from, right? So 8.89 times 10 to the minus 3 divided by 0.25 times 100% is equal to 3.5%. So that's good enough, right? So X then gives me the concentration of H3O plus. So pH is equal to minus the log. So this is, sorry, H3O plus concentration minus the log of 8.89 times 10 to the minus 3 is equal to 2.05. Okay, and by the way, always think about your answer, right? This is a weak acid. You should have a pH that's low, right? An acidic pH. If you solve this problem and you get a pH of 10, you should go, wait a minute, something's wrong, right? I should have an acidic pH when I have a weak acid, right? Okay, questions? Any questions? Okay, good. Awesome. Let me define percent ionization. And the percent of ionization is the concentration of H3O plus divided by the concentration of HA initial times 100%, right? So this gives you sort of the number of acid molecules per 100 that have ionized. So for example, if I have an acid like hydrofluoric acid, let's say, HF, and if I have a percent ionization of 10%, what that means is that 10 out of the 100 molecules have ionized, right? It means that I would have, 10 H3O plus, 10 F minus, and 90 HF in solution, right? It would be a mixture of 90 of these plus 10 of these, which means that out of 100, 10 of them ionized, right? Oops. Out of 100, 10 of them ionized, right? Does that make sense? Let's see. Remember, for a weak acid, right? For a weak acid, when you put HF in the water, a lot of them remain unionized, right? And some of them actually ionize into H3O plus and F minus. So the percent ionization is how many of them out of 100 have ionized? How many of them have broken up into H3O plus plus F minus. That's what that means. Does that make sense conceptually? Let me find out where we were here. Yeah. So percent ionization is the molarity of the acid divided by the initial molarity of the ionized acid divided by the initial molarity, right? Now, since for many weak acids, right, the percent ionization is pretty small. In other words, you can make for those weak acids in which you can make the exit small approximation, you can just use the initial HA concentration here and the H3O plus concentration here. All right. So that's what this formula is giving you. H3O plus at equilibrium divided by HA initial. All right. So let's just do an example from what we already calculated, right? So for that nicotinic acid, right, I had 0.012 molar. And the H3O plus concentration, when I solved for it, was 4.1 times 10 to the minus 4 molar, right? So my percent ionization is equal to what? This, 4.1 times 10 to the minus 4 molar divided by my initial concentration. Okay? And in that case, that turns out to be 3.45%. So about 3.5% of the molecules ionized there. If I were to do the same thing for a 0.12 molar solution of nicotinic acid, I would find that the H3O plus concentration in that case would be 1.3 times 10 to the minus 3 molar, okay? So for a 0.12 molar, I get that. And what I want you to see here is the following, and this is a little subtle, but I've increased the concentration of the acid by a factor of 10, right? And going from there to there. The concentration of H3O plus increased. So in other words, the solution got more acidic, but it did not increase by a factor of 10. Okay? And what that means is that if I calculate the percent ionization for this one, right? 1.3 times 10 to the minus 3 molar divided by 0.12, I get, times 100%, I get 1.08%. So look what happened to the percent ionization. It actually went down. Okay, so in other words, percent ionization depends on initial concentration of my weak acid, right? Percent ionization depends on my initial concentration of the weak acid. Furthermore, as concentration of HA increases, what did we see happen to percent ionization? It went down, right? As HA increases, percent ionization decreases. Okay? But now, I don't want you to confuse that with the idea that somehow as the concentration gets greater, the solution becomes less acidic. That is not true, right? Look at the acidities here, right? When I increase the concentration from 0.012 to 0.12, right? Look what happened. It did get more acidic as I would expect, right? As I make the weak acid more concentrated, the solution becomes more acidic. That makes sense, yeah? That is always the case. But nonetheless, the percent ionization went down. Okay. All right, so let me see if that's
Hey, Tro, why is that?
yeah, that's a great question. You can make this kind of argument. If I have a weak acid HA plus H2O goes to H3O plus A minus, this is aqueous, right? As I make the concentration more concentrated, right? I form more of these, and that tends to push the equilibrium to the left. Or another way to say it is, as a solution becomes more dilute, I have less particles ionized, and that tends to push the equilibrium to the right.
Oh, okay, that makes sense.
Yeah, it's not a totally satisfactory answer, but it's kind of good enough. Okay. Now in this one, let's just do one last example just to nail this home, right? Again, don't overthink this. It's really easy. You just take the initial concentration, put it in the denominator. You take the concentration of H3O plus, put it in the numerator. Now here I'm giving it to you. Normally you would have to calculate that by doing an ice table problem, right? Like we did earlier for HClO2, right? And then you multiply that by 100%, right? And in this case, I get 28%. So you can kind of see the range for these percent ionization. Most weak acids are going to be in this range, right? Are going to be a few percent or less. This happens to be a weak acid with a fairly large Ka, and so it has a pretty high percent ionization, right? And of course, what would the percent ionization be for a strong acid?
Nearly 100%.
Nearly
Right.
100, essentially 100%, yeah. For a strong acid, percent ionization is 100% because every single molecule ionizes, right? Does that make sense? Okay. Let's see if you're getting this. Here's a question for you. I don't want you to have to work an equilibrium problem or anything here. Just think about it. Remember that the more acidic a solution is, the lower the pH, right? A low pH means acidic. 7 is neutral. High pH is basic. So another way to think about this question, if you're having trouble here, which solution would you expect to have the lowest pH? Which solution would you expect to be the most acidic? Right? Which one do you expect to be the most acidic? Don't overthink this. Okay, let me ask you this. If I had a bunch of strong acid solutions, let's say I had 0.01 molar HCl, 0.1 molar HCl, sorry, and 1.0 molar HCl, right? A, B, C. Out of these three solutions, which is the most acidic?
C, right?
C, right? The more concentrated one, right? As the acid gets more concentrated, the solution gets more acidic, okay? If these are weak acids, right? Let's say 0.01 molar HCHO2, 0.1 molar HCHO2, 1.0 molar HCHO2, right? Which one is more acidic?
C.
Still C, right? Doesn't matter if it's a strong or a weak acid, the more concentrated it is, the more acidic the solution, right? And the lower the pH. Of course, if I compare this one and this one, out of these two, which is more acidic? The strong one or the weak one?
Strong.
Strong one. Okay. Strong one is more acidic. All right. So don't get percent ionization confused with the strength, with the pH reading and how acidic a solution is. Okay. It's always the case that when you take a strong acid or a weak acid, as it gets more concentrated, the solution gets more acidic and the pH gets lower. All right. So what's the answer to this question? What's the correct answer?
So then it's D.
So it's D, right? It's D, because that's the one. And a lot of you got it, but some of you put A. But again, that's probably because you were overthinking it and you were thinking percent ionization. Okay. Percent ionization is a secondary sort of effect. The most important thing is pH. As it gets more concentrated, it gets more acidic and pH goes down. Okay. Now answer this question. All right, 10 more seconds. All right, very good. Nearly perfect. The right answer was A, and 94% of you got that. Okay, so those are both true. This has the highest percent ionization, but this has the lowest pH or the most acidic. Okay, those are both true. All righty. Questions? Taylor, did you have a question?
Yeah, so if you're given the percent the percent ionization,
Yeah.
can you figure out your K of A?
Yep.
Because you're given like the
Yep.
equilibrium.
Totally.
over the
Right. You
initial-
plug that
okay.
into the equilibrium constant expression, you can get Ka from that. Absolutely.
Okay.
Yep. Good.
That's handy.
Good. All right. Let's look at base solutions. We've spent a lot of time looking at acid solutions. Now let's have a look at some base solutions. And we'll start out, just like we started out with acids, we'll start out by looking at strong bases. Okay. So for a strong base, we have something like NaOH, let's say. right? When you put NaOH in the water, it completely ionizes, right? So if I have 0.10 molar NaOH, right? That breaks up into Na plus OH minus, right? So my OH minus concentration is equal to 0.10 molar. All right, and if I want to find the pH of that, I can just get POH first is minus the log of 0.10, right? So that's equal to 1, right? Yeah, 10 to the minus 1, that's equal to 1, right? And then if I want pH, right, I can use pH plus POH, pH plus POH is equal to 14. So pH is equal to 14 minus 1 is equal to 13. All right, so sometimes if you're dealing with OH minus, just get the POH and then subtract from 14 and that'll give you the pH. The pH scale is more common, right? So most of the problems are going to ask for pH, even in a basic solution. All right, so notice strong base, pH very high, right? That indicates very basic. Yeah? Okay, so now there are some bases like this one that produce 2 OH minuses per mole of base, right? So something like SrOH2, when it ionizes, is going to form Sr2 plus 2 OH minus. So what's the concentration of OH minus in this solution? Well, if that's 0.0015 molar strontium hydroxide, then the concentration of OH minus is what? 2 times 0.0015, right? And that's equal to 0.0030 molar, right? So again, I can just take my POH, and that comes out to be equal to, I did it differently. Let me just figure that out. That's 0.003, and then I want to take the log of that. All right, so POH is equal to, so POH is equal to 2.52, so pH is equal to that minus 14, so pH is equal to 11.48. Okay. Does that make sense? Yeah, pH is minus the 2.52 is just minus the log of that. So POH is minus the log of 0.0030. Right? So the definition of pH is minus the log of H3O plus. The definition of POH is minus the log of OH minus. And then we know that pH plus POH equals 14. Okay. All right, good. Yeah, it's just the same thing. Just kind of worked out. I tend to like it. I tend to like to work it out on paper, but it slows me down. If I go through this, I go too fast. Okay, what about weak bases? Well, just like, so for a strong acid, right, we can get pH directly from the concentration of the strong acid. For a strong base, right, it's the same thing. I can get pH directly from the concentration of the strong base, right? For a weak acid, I had to solve an equilibrium problem. For a weak base, I have to solve an equilibrium problem, okay? So so far, right, we've been using this equation for the weak acid equilibrium problem, right? This is your first best friend, and here's your second best friend, the ionization equation for a weak base. Okay, so it's B plus H2O in equilibrium with BH plus OH minus. Let me let me write this a different way, just so I write it the same way every time and it doesn't get confusing. I want to write it in parallel to this one, so I'm going to write it like this instead. It's the same exact equation. Okay, but I'm just going to flip those two around. Okay, just because that way H3O is here and OH minus is here, and then they're more analogous. All right, because we're going to be using these two equations a lot. So I'm going to call this equation number 1, and I'm going to call this equation number 2. Okay. All right, so notice how a weak base works. A weak base works by taking a proton from water and forming OH minus that way. Okay, so here you see ammonia acting as a weak base. It's taking a proton from water. And again, I should flip these and put them the other way, but it's OH minus and NH4 plus. Okay, so here's a bunch of weak bases and their corresponding KBs, right? So KB is the base ionization constant, right? And it's going to be equal to the concentration of OH minus times the concentration of BH plus divided by the concentration of B, right? It's just the equilibrium constant for that equation. Okay, so all of this is analogous to what we just did for weak acids, but now we're applying it to weak bases, right? And so here are some weak bases. They all work in exactly the same way. They all take a proton from water, right, and form BH plus OH minus. Here's ammonia, water, take a proton, and there's the KB. Okay, so let's do an example. So morphine, remember I was telling you that a lot of plant-based toxic substances are bases, right? And morphine is one of them. Morphine is an active compound in humans, right? It's used in medicine under extreme circumstances. Why? Because it allows the relief of intense pain, right? Of course, in too high amount, morphine is deadly, right? It'll kill you in too high of amount, which is why people can overdose on morphine. Some people use morphine recreationally, but really, what its main use is in cases of extreme pain. Cancer patients, people that are in constant pain, will be given morphine because it alleviates that pain. Okay, but it is a base. Okay, and notice I didn't give you the formula of morphine, but you can just write this generic equation: B plus. It works like every other base, right? And I'm going to do OH minus plus BH plus, okay? And I'm given KB for this base is 1.6 times 10 to the minus 6, right? And I want to find pH, right? So I set up my ICE table, right? It's a weak base. I got to solve an equilibrium problem, right? It's very much the same thing as what we've been doing. 0.0015 molar. 0 and 0, minus x, 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 0.0015 minus x, x, x. So I get x squared over 0.0015 minus x is equal to KB, 1.6 times 10 to the minus 6. I'm going to make my x a small approximation. Solve that for x. I get that x is equal to 4.9 times 10 to the minus 5. Okay, and then I want to check my x's small approximation. 4.9 times 10 to the minus 5 divided by 0.0015, because that is kind of a dilute initial concentration, right? but if I multiply that out, I find that that's equal to 3.8%, right? So I'm good, okay? So this is X. Now, when you solve an equation using a weak base, the X is not equal to the H3O plus concentration. It's equal to the OH minus concentration, right? So I know that OH minus is equal to 4.9 times 10 to the minus 5, right? So I take minus the log of that, which is equal to POH. I get 4.31 for POH, but the problem asks for pH. So pH is equal to 9.69, right? And how do I get the 9.69? I know that pH plus POH is equal to 14, right? So pH is equal to 14 minus 4.31, which gives me 9.69. Does that make sense? Here it is worked. Here's a second review for you. So minus X, 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 0.00015 minus X. So you get that. You got KB. Make the X's small. This is like the instant replay. So you get X is equal to 4.9 times 10 to the minus 5. So that's less than 3.3%. So the approximation is valid. So the morphine concentration is that. pH plus concentration is, OH minus concentration is that. So another way you can do this problem, right, if you wanted to, was instead of finding the POH, you can find the H3O plus concentration, right? Because the product of those two is going to be equal to KW. So you can find the H3O plus concentration, take minus the log of that, and that gives you the same number, right? You could do it either way. There's the POH. Okay, great. Okay, cool. We're right up to where we need to be.